As you may know, sea ice is a major component of the climate system due to the role it plays in the Earth's energy and water budgets. Its extent has decreased in all months over the past 30 years, particularly during summer, reaching levels that likely have not been seen in several thousands of years. This decline is faster than what most models have forecasted, and scientists fear that we'll reach nearly ice-free summers in the coming decades. That is why it is essential to understand the science of forecasting and to improve our skills to do it. There are several physical mechanisms that can offer predictability, but the one that we chose to use is the persistence of the Arctic sea ice anomaly. Persistence is the first source of predictability for the ice anomalies and is defined as the time necessary for a time series to decorrelate from itself. But what did we do exactly? Let's begin. We begin, of course, by taking data. These come from these websites, which provides a lot of information about the evolution of Arctic sea ice. The simplest prediction, and the first we did, is made by computing the trend line, fitting the previous data of September sea ice extents, and extrapolate the data for 2021. This graph makes it easier to understand the decrease in the Arctic GIF you saw earlier in this video. But this is kindergarten level prediction, and after 1 year studying climate physics, we can do much better. Now it is time for us to use this persistence we talked about earlier and do what's called an anomaly persistent forecast. If we assume that the May anomaly will persist until September, we can find an expression of the forecast very easily, as you see here. Because the atmosphere, and especially the ocean, vary slowly, except in special circumstances, this sort of forecast usually has a skill that is not so bad. It is clear when seeing this graph that our first model is not perfect at all. We will define later a score that allows us to measure our model's quality. But to do that, and you will understand why, we first need to define an event. And the one we choose is the following. September Arctic sea ice extents will be less than previous years. Now this is where it gets a little bit more technical, but you'll see that we use exactly the same kinds of graphs for every improvement of the model, so please don't panic. The graph on the left represents the probability that our event happens. If the event actually occurred, the bar is blue. The ideal forecast will have big blue bars and small red bars. The graph on the right is the same as before, but with the whole probability density function instead of the 95% confidence interval. We defined the PDF as a Gaussian. The standard deviation of each PDF is very small, meaning that our model is very sure about itself, such that a small difference between observations and projections is enough to force the probability to take extreme values, close to 1 or 0. In the histogram, we see that our model has high precision but low accuracy, which is basically the worst case scenario in terms of modelization. Now it is time to introduce a way to measure the quality of our models, called the Brier score. It is a quadratic measure of error in probabilistic forecasts. For a set of n forecasts, it is defined by this formula, where p is a probability that the event occurs between 0 and 1, and O are verifying observations for the events, 0 or 1. The score that we will use is the Brier Scale Score, or BSS. It represents the level of improvement of the Brier score compared to a reference forecast strategy, and is designed to range from 1 for a perfect forecast, through 0 for one that provides no improvement over the reference, to negative values for the ones that are worse than the reference. If you want to know more about this, there is a wiki link in the description down below. But to understand this video, all you need to keep in mind is that a good forecast should always have a BSS that is positive. And that is what we are trying to reach. As you can see on this graph, we still need a few improvements to apply to our model. It is indeed a good start for understanding what a forecast is and how verification works, but the results are disappointing, and we can do much better. We will now try to build an upgraded model that fits better the observations and has more uncertainty. To do so, we now take into account not only the data of May, but also from all the other months of the year. We also add an error of 500,000 square kilometers on the observations of the sea ice extent, to be more realistic. Now, let us see what happens. Looking at the four same graphs, we see that our forecast is now more able to well predict our events. The values taken by the probabilities are now much more likely, as we almost don't have any extreme values left. Indeed, the standard deviation of each PDF is bigger, thanks to the error we add. Another indication that the upgraded forecast is better comes from the BSS. It has now on average a value of about 0.3, which is much more interesting. However, we can see in every graph a strange break in the behavior between before and after 2007. What happened at that moment? In the literature, scientists show that there is a before and after 2007 when it comes to the Arctic sea ice extent behavior. It is interesting here to see that although our model is very simple, this break can be clearly identified. Our statistical model prediction is now good, but in the process of forecasting, one last step is missing, the post-processing. We will now do what's called a pro-gamer move. Please do not try this at home. Post-processing is just an intelligent way to say that we are going to cheat by adding some of the projections because our model isn't good enough. For example, after 2007, the forecast systematically overestimates the true value of SIE. Basically, the way it works is that we reduce every projection after 2007 by a certain amount so that the mean of the projections matches the mean of the observations for the period after 2007. Doing so, the forecast has now become very good because the systematic overestimation from after 2007 is now gone. Furthermore, our 95% confidence interval now matches all observations, even the extreme events of 2007 and 2012. Break that once was here for the probabilities has now also disappeared. Our BSS is about 0.3 for 2020. It is now very good for our little statistical prediction model. Something that's usually very interesting to do is to remove the time dependence and plot the observations in terms of the forecasts. Making a linear regression in the set of points will give the true trend of our forecast model. This simply means that if, for example, our model that was not post-processed predicts 5 million km² of SIE in 2021, it will rather correspond to 4 million km² than the 5 million km² initially expected. As you can see, the results are much better after we change the post-2007 behavior. Although this method can seem to be incredible in terms of results, it has some serious downsides. The biggest one is that this method is only based on the difference between the forecasts and the observations and not on some physical evidence. Therefore, this artifice will quickly lose relevance with years, so we need to keep that in mind. Moreover, we are constantly overfitting the data. Indeed, we took all the data available for our forecasts, and we have done the verification of this exact same data. In addition, our sample of data is small, and it is a serious limitation. To finish this video, let us take a look at our 2021 September sea ice forecast, since it is the main purpose of what we are doing here. What you see here is a 95% confidence interval of our forecast. Indeed, if there is one thing that we'd like you to remember, it is that a forecast is never a single value. It is a probability density function. No one is able to tell with 100% confidence that it will rain tomorrow, or that we will face an Arctic ice free next year, because nothing is certain.